Hi everyone, welcome to the Module 7 instructor presentation. Where I will be going through some of the themes and concepts of Module 7, and you can see those listed here, which will include essentially an analysis of the auditory system, where we'll go over the physical and perceptual dimensions of sound, some of that anatomy and physiology that we've been doing throughout the course. I also want to make sure that you constantly think about how this relates to the other visual system, to the visual system. Um, the auditory system has similarities to it, and there's also differences and so forth, and we'll try to touch on that a little bit. Of course, cover some of that pathology when things go wrong, so to speak. And once again, the common theme throughout the course really is that our perceptions are ultimately the result of how our nervous system works. So without further ado, let's jump right into that. The physical and perceptual aspects of sound perception. First off, just like vision, you have a physical stimulus, and that would be the more objective way to study sound. So we can study literally the stimulus or pressure changes in the air or some sort of medium like water. That's literally the beginning there. There's just changes in air pressure that alternate from high and low pressures, essentially. And then we have the perceptual definition, which is the actual experience that we have. You know, different types of voices, different kinds of music, all of that. And you can see here, there's a speaker, a little tiny, what looks like a bookshelf speaker with its little diaphragm there, is essentially, as it alternates back and forth at certain frequencies, is creating differences and it's creating these variations in sound pressure changes, where you have high and low pressure, essentially. Air molecules are being alternating between being crammed together and being pulled apart. And that's what it's doing, essentially. And that's what the definition here is. The diaphragm of the speaker moves in and out. And, um, and that's essentially what it's doing. And one thing, and if we measure these pressure changes over time, and if it's a certain type of sound wave, you get what's called a pure tone. All right. And if I plot a pure tone, you can see it right there. There's a sine wave. This is looks like it's Wikipedia. That's fine. Or I'll just do any of these pictures here that'll look good. This is a sine wave, where this would be high pressure, low pressure, high, low, alternating. Um, and this is essentially the sine wave. If we're measuring a sound, if a sound wave happens to show this pattern, it's called a pure tone, and it's essentially one of the most simple forms of sound that we can experience, essentially. But I'm mentioning that because your author goes into that throughout the chapter, and there's the pure tone. Um, Sound is measured, of course, in frequencies, hertz, which is one cycle, which is a cycle that we've just seen here. One cycle, that's a cycle. Um, this corresponds, you can see here, to the grating stimuli that was mentioned earlier in the text, so that's a nice comparison there. And you'll see with sound, we have amplitude and we have frequency. How many of these pressure changes, these alternating pressure changes, do we have in a given area? And that's what we define as frequency and of the sound. So here you can see different, this is a higher frequency, maybe a mid-range, and this is lower. And these have correspondingly different perceptions. This would be a higher pitch, like a higher pitch voice, generally females have a higher pitch voice than males have a lower pitch voice. And so there's a physical difference there. And that's also shown here. Here, the amplitude of the wave, which is the height, where it can maximally reach, is different. And this is associated with loudness. It's not the only factor, and you have, of course, there's a part of the course you explore this a bit more. Amplitude is significant. So when you're turning up your iPhone, listening to music, if you're turning that volume up, you're essentially making the amplitude of the wave larger. And you can see and it's measured in decibels, which I'm not going to get into too much here, but decibels are a way to measure where we have 0, which is barely audible, to pain, which is jet engines taking off. You don't want to have your ears near that, and you can see some differences here. About 60 decibels is about where I'm at right now. That's a speaking voice. Okay. Um, some of these I don't want to get into, but one thing, when you look in your text, be sure to notice that, we have typically a voice, music or whatever, is complex. So it's made up of lots of different waves, lots of different waveforms are combined, and this can be analyzed mathematically, but we're not doing that here. But the primary wave is what we refer to as the fundamental frequency. Then there's a lot of other stuff that's kind of associated with it. We call it harmonics, which is kind of interesting. So when you listen to different music, as an example, um, different instruments can sound different, even if they're playing the same notes, essentially, because the harmonics are different. So an electric guitar adds more harmonics to the sound, which gives it more of an edgier sound, a more intense sound than listening to, let's say, an acoustic, which is a bit more of a pure type of sound. And if you, a flute, for example, is about as pure of a sound you can get versus, let's say, an electric guitar, which has, like I said, has a bit more, has more of these harmonics associated with it. And this is shown here. These are the, I'll zoom that in a tiny bit, but here you can see this is, essentially this waveform on the top here is a combination of these other ones down the bottom. And the reason why your author is showing this is because one theory is that essentially the auditory system analyzes this complex waveform and breaks it down into its components. That's one possible thing that your ear does. That's one possible thing. In other words, it's a frequency analyzer. It's kind of interesting. But typically, though, these are more like pure tones, but they're different frequencies and stuff. But but ultimately, this complex wave is a combination of different. It's a combination of different waveforms. They're added together to form a more complex sound. And here, of course, is I mentioned loudness. Measure in decibels. Once again, go through that material on the audibility curve, and I have another, I can zip through that kind of quickly here, but essentially that audibility curve defines what we can hear. And this is the range of hearing, by the way, 20 to 20,000 hertz, all right? So 20,000 hertz is really high, and I have that activity for you to see if you can hear all those different tones. As we get older, our ability to hear the higher frequencies diminishes, all right? So I can share with you, and my students always, some of them think it's sort of funny. I'm not sure why. I guess because I'm getting older, but at around 12 or 13,000 hertz or kilohertz, I have a harder time hearing that kind of stuff. I'm not afraid to admit I'm well past 30 at this point. I'm approaching 50, to be honest with you. And as you get older, the higher frequencies are more difficult to hear. Most of my students, if I'm teaching this on campus, and whatnot, they are younger. They can generally hear close. Some of them can hear up to 20,000, but not everyone can hear that. It's sort of interesting. But we are more sensitive to these ranges in here. All right, just to make a long story short, essentially. This is conversational speech. So when you think about the auditory system, think about the context in which it evolved. It evolved. Sure, music is great. I love music. I enjoy going to concerts. I enjoy all that kind of stuff. I enjoy going to movies and experiencing those sounds. But ultimately, our auditory system likely evolved to communicate. In other words, we have to hear people. We have to hear ourselves. We got to get that feedback ourselves. And this is the typical range, plus or minus a little bit, of conversational speech. So that's one of the reasons. And there's, of course, once again, you can go through the equal loudness curves and stuff like that. This is basically going through that sounds as we go through the 20 to, in this case, we're seeing it at 10,000. We are not equally sensitive to all that 20 to 20,000 hertz. We are more sensitive to what's called the mid-range. All right, that's essentially what they're showing there. The low frequencies, this is your bass, and these are the higher frequencies. This would be like your treble. Generally, what we need to do is boost those a bit so that they can become, so we can hear them, essentially. And that's what that curve is showing. Yes, and of course, that's the frequency. We just, talking about frequency, the subjective experience is pitch. Once again, bass versus treble, stuff like that. Now, what about the physiology? All right, so make sure when you're going through here, there's, the book does a great job explaining the different parts of the ear. And just like the visual system, you have transduction occurring. You've got to get that physical stimulus converted to action potentials. And that's really what the ear does, amongst a lot of other things. And there's different parts. You can see the picture here. You got the outer ear, the middle ear, and the inner ear. But essentially, the outer ear is going to funnel those sound waves. Okay, so you got your earlobe there, which is called the pinna. It's going to funnel those sound waves. And ultimately, it's going to stimulate this middle ear part. And then that middle ear is going to stimulate, I'll zoom in a little bit, it's going to stimulate this snail-looking structure. This is the cochlea. All right, cochlea gets stimulated, and ultimately the transduction occurs here where my pointer is. These semicircular canals are actually, just to let you know, they're not part of the auditory system. They're part of the vestibular system. They're involved with balance, but they are connected. And then there you can see the auditory nerve. It's connected to the cochlea, and it's going to send those signals off after they've been, it's going to send those signals off to the brain. And you can look through here and see the different parts, but um, essentially zooming in on the middle ear, you've got the malleus, incus, and the stapes. And this does a quite effective job of transferring that energy into the middle ear, excuse me, into the outer ear. God, I keep saying it, the inner ear, pardon me. So we go from the middle to the inner, and this is the outer part, all right? There's the tympanic membrane that this vibrates, and this is going to vibrate more or less, it's going to resonate with whatever frequencies you're listening to, and it's going to push these guys. And what that does is this little tiny bone there can really press nicely on that oval window. And that's what they're showing there. The area of the stapes, that's the foot plate, is quite small, and that really confers a lot of pressure. It does a great job of transferring. Um, and then here you can see ossicles, those are those middle ear bone, help amplify the vibration for better transmission to the inner ear. The outer and the middle ear is air-filled. The inner ear is fluid-filled, just to let you know. And then here you can see the inner ear. It's got a cochlea. It's very small, about 35 millimeters long. And it's, you can see here, the real action here is essentially the cochlea. What's happening here is fluid is flowing in here, and it's going to vibrate, and it's going to tend, and let's jump right there. You can see it's going to pull along these hair cells that are located in there. All right, so this is the basilar membrane that's located in the cochlea. Basilar just means floor, and the tectorial membrane, tectum in Latin, is roof. So this is the roof, and so you got the roof and the base there, and they're moving back and forth. So you can see this is going back and forth. The basilar membrane is going up and down, and then here we have the hair cells, and I'll zoom in on them a little bit. Those are the hair cells, and those hair cells, when these little, they almost look like little stubble of hair. When they move back and forth, they cause the auditory, receptors in here to produce action potentials, and that ultimately sends signals off to the brain, as we hear things. Okay. So once again, the basilar membrane tends to vibrate. That basilar membrane is quite important. If it starts to, if it gets damaged, that can result in hearing loss, essentially. So transduction, make sure you pay attention to that. Those little hair stubble, they're more appropriately called cilia. Okay, and they basically cause receptor potentials. Now, what is the importance here of the basilar membrane? Well, a researcher named Bekesi back in the 1950s figured out how the cochlea works. He figured out, in particular, how the basilar membrane works. And so this is explained nicely in your text, so make sure you go over that. Essentially, it vibrates, and these are some of the drawings that he did. And as we hear different sounds, the basilar membrane sort of flops up and down. And depending on the sound we listen to, it's going to we're going to tend to see greater or lesser amounts of this distension at different parts of the membrane, essentially. So at this particular sound, we're going to see distension here. If I listen to a different sound, I might see more distension over here or more towards the apex. And it turns out that it's relatively predictable. As we get more distension here at the apex, it's more associated with lower frequency sounds like bass. Closer to the base, you get more, if there's more vibration here, it sounds more like the higher pitch. And that's what he basically found. There's this interesting wave-like motion that occurs. Okay, and that's really what he found. This all was, and he found essentially a map, what we call a tonotopic map, this mapping of sound frequencies, and that's shown here. So depending on where you're at in the cochlea, you get more activity. Let's say like here at 6,000 hertz, this is going to tend to make this part of the cochlea more active, essentially. Here's 5,000, here's 4, and it's nice and predictable all the way around, all the way around. This all supports what we call the place theory. But once again, just like the visual system, remember the visual system had a retinotopic map, which was a literal map of the retina. Here we have a tonotopic map, which is a map of sound frequencies. Very interesting. Once again, apex responds best to low frequency sounds like bass, and the base responds best to higher frequency sounds. That's not the whole story in terms of how we perceive different pitches, but it's a big part of it. All right? And it turns out that we have in the cortex neurons that are tuned, they're broadly tuned, but they're tuned to different sound frequencies. So you might have a particular neuron in your cortex of the brain that responds best to a bass sound, or it tends to respond best to a higher frequency sound, and so forth. So this is all evidence of what we call the place theory. All right. And so once again, you go through that and look at that, but it's very interesting. Um, and that's not that's the main thing I want to go over here. But essentially, uh, what we find is that this basilar membrane is very interesting. It might actually be doing what's called a frequency analysis. It tends to, you know, when you're listening to different sounds, you have, let's say, those complex harmonics I was talking about. You're going to have different activity of that membrane depending on the particular harmonics you're exposed to, and that's what they're showing there a little bit. Be aware of the pathway in the brain. Right, there's a little bit of this in the text, and you're seeing that essentially there's the cochlear nucleus. This is receiving signals from the auditory nerve, and then basically the projections you can see. Some of them are what we say ipsilateral, means it stays on the same side of the brain, and some of them go to the other side of the brain. But essentially, like the other sensory systems, you've got signals that arrive at the thalamus, and then from the thalamus to the cortex. Um, so you have the medial geniculate of the thalamus in this case, as opposed to the dorsolateral geniculate for the visual system. And then ultimately this goes off to the temporal lobe for further processing, and that's shown here. So here you can see this is the human brain on the top, and this is the monkey brain on the bottom. Here's the temporal lobe. Bottom part of the temporal lobe here is for doing more visual system stuff. Up here, though, we got different areas. This is the top part of the temporal lobe involved in auditory analysis so that we know what a sound is. Remember, like the visual system, we've got, and it's not showing here, but you have essentially what and where divisions in the brain, where this part here is going to be more of the what. What is the sound I'm listening to? And one of the main ways we determine what a sound is through a frequency analysis. But then there's also sound localization, which I'm not getting much into here, but then other parts of the brain are involved with actually locating where is that sound? Is that mosquito buzzing behind me? Is it right next to my right ear? Is it my left ear? That's another aspect. But like the visual system, we've got to do what and where. And here we're seeing an analysis of what essentially there, at least parts of the brain that do that. But essentially, here's more evidence. You can see pitch in the brain, and this would be humans, I believe. I think that's, but essentially, you have different parts of the brain that respond to different different pitches, whether it's a high pitch or a low pitch, where we see differential response. So once again, this is very similar to what we see in the visual system. Okay, now we're at I've already hinted at this a little bit. What about the problems? What about the pathology? Well, presbycusis, and we have a parallel for this in the visual system as well, which was a presbyopia, essentially the hardening of the lens. Your visual acuity tends to drop when you get past 40. Well, here we have the same kind of thing for the auditory system. Presbycusis is a stiffening up of that basilar membrane, and that basilar membrane, as it gets stiffer in certain parts, you have a harder time hearing things, and that's the high frequency loss. This is what I have, and anyone my age is going to probably have this, and it just gets worse with age. Sorry to say, but it's interesting though, because I have some loss, but I don't really notice it unless I'm taking those tests. I put on music, it doesn't really sound different to me. Although I would imagine if I put on one of my albums and I was able to do a Back to the Future or something, go back in time and be 15 years old again, it probably would sound better. That's my guess. But we lose at those high frequencies. Tends to affect males more than females, interestingly enough. This is interesting. Drug use might actually cause this and make it really severe. But certainly damage, if you go to a lot of concerts or where you're exposed, if the concerts are loud, you're going to tend to work that basilar membrane and cause damage to the hair cells there. And it's going to tend to cause greater hearing loss, just to let you know. You could have noise-induced hearing loss. This could be, folks that work in really loud jobs. I used to teach out in Oklahoma near a place called Fort Sill, and they did and a lot of the soldiers there. It was an artillery training area, so they were constantly blowing stuff up, and they wear protective gear, but there's no doubt in my mind that they were damaging their ears doing that because that's really, really loud. I mean, even just the regular urban noises when you're in a city can cause noise-induced hearing loss, essentially, and that's what they're showing you here. That you're getting, they're just showing some data here that after a while we're getting less and less response to the sound and the auditory nerve, essentially due to exposure to loud noises. One way to help for this is essentially we can get a cochlear implant. This is There's also, of course, hearing aids. Hearing aids are for regular hearing loss, hearing aids are the best. And those hearing aids are just very fancy amplifiers, essentially. It doesn't really solve the problem. It just helps out for folks. But some folks that have maybe more severe damage where the cochlea has been completely damaged, where they cannot, this is where they just can't hear anymore. You can get an implant, which essentially is trying to do the work of the basilar membrane, um, which is complicated. So this is why an understanding of how this works can help make these devices better. But you can see this is essentially, this coil is in there. This electrode is in there essentially trying to do the job of the cochlea, and then it's going to cause the stimulation of the auditory nerve. It's very interesting. I know that a lot of folks that use these, I know historically, they're really geared to try to make sure that you can at least hear people, and they're gearing towards getting people that have had deafness to be able to communicate. I'm not so sure how well they work, like appreciating music. That's very tough. Music has a very complex waveform. If you're listening to a symphony or rock music, whatever the case may be, you got really complicated waveforms that have to be interpreted by the brain. And that starts with this basilar membrane, right? It starts with that basilar membrane. Yes, that's, anyhow, I hope that this helped a little bit. Please, obviously in the class, if you have questions, direct them to your instructor. And I hope you have a great week. Take care.